What's up, guys? This is Drew, and I am the SDSU EE tutor. I want to run through a couple of sample problems that may possibly show up on the midterm. Alright, so these weird things. These take you through the different stages of your pipeline. Alright, so just real quick as a refresh, fetch, this gets the instruction. So this just reads the ones and zeros and sees what instruction it is. Decode, this guy reads from the registers. So if you're using registers such as RA and RB, you need to read that value. That'll happen in the decode stage. Execute is when any math happens. This involves the ALU, the arithmetic logic unit. If you need to do any type of math, whether it be adding registers, subtracting registers, or incrementing registers, that is done in this stage. Memory reads or writes to memory, and that would look like D. You'll see instructions that have D, R, B, something similar to this. And this should look familiar because we've been playing with E, B, P. Alright, so hopefully this should look familiar. And this format says this is going to be 8 plus the address of EBP, right? Plus EBP. So really this is an address, so this is just like 0x51370. So this thing says 8 plus this, and that'll give us 51378. Right? Realize this is an address. So if you see this format, we're talking about memory. Writeback, this updates registers. So for example, in this register to register move L, you're writing to register B, right? You're taking what's in register A and you're moving that to register B. The writeback stage is when that value gets moved to register B. And PC update, this moves the program counter to the next instruction. So say we've got this snapshot of memory. These are different addresses, and these are the instructions stored in those addresses. So the green is one instruction, and then the orange is the second instruction. These are 2 bytes per instruction. Right, this is 1 byte, and this is 1 byte. So 2 bytes per instruction. Originally, program counter is pointing here. When we want to move to the next instruction, that means we want program counter pointing to the spot where the address where the orange is. So that will be PC plus 2. So originally program counter was 0010. Then if we increment it by 2 and just add 2, right, 2, then we're going to get 0, 0, add a 1, 1, 0. Right, we're going to get this address. So that's what we do in PC update, is you increment the program counter by however long your instruction is. Now that we've gone through the intro, let's get started. Before we start the problem, let's write this guy in ones and zeros based on our instruction set architecture from the book. So we said we're using a register to register move L, and it tells us that for this instruction code should be 2. Okay, so 0, 0, 1, 0, this is 2, and fun should be 0. 0, 0, 0, 0. Notice this is 1 byte, right? And it encapsulates code and then fun. So then next it has registers, so we are going to be using the next byte for register A and register B. Register A, let's see, what do we have to pick from? So down here, you'll have something that maps the different registers to different numbers. So let's do EAX and ECX. So 0 and 1. 0, 0, 0, 0, 0, 0, 0, 1. And this is RA, RB. This is iCode, iFun. And for this instruction, that's it. We don't have anything else. It's only 2 bytes. So now if we head back to these guys, let's see if we can start coding this thing. So this will be iCode and iFun. And then the notation that we use is this little arrow thing, and we say this is going to equal M1 PC. So we're going to read iCode and iFun, which is 1 byte of memory stored at the address of the program counter. So the program counter is pointing to this instruction right here. And we said it is 1 byte in memory stored at the address of PC. So this is how we know where iCode and iFun are. So every single time we do these types of problems, everyone will have an iCode and an iFun. The next question we have to ask is, does it use any registers? And if it uses registers, then we need to have a value for RA and RB. And this does indeed use registers, right? Is a register to register move L. So we're going to have RA, RB, the little arrow thing, and this is going to be 1 byte in memory stored at the program counter plus 1. Alright, so if we go back to this guy, right, program counter is here, program counter plus 1 would be right there. And we said we're reading 1 byte in memory, and this is going to be RA and RB. The next question is, do we have a val C? No, we don't have a val C, because val C stores this information. It stores the constant, right? So IR move L would be move a constant to a register, so that's like $5 to EAX or something. Val C is this 5 in 4 bytes, so it would be 0, 0, 0, 0, dot, 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 all the zeros up until 0, 1, 0, 1. So no, we don't need a val C. The last question is, what is val P going to be? Val P. So this is also done in every single instruction. You will need to update the program counter. So you will always need a val P. So val P will be equal to program counter, the current program counter, plus however long our instruction was. So if we look back up here, we said this was M1. We're reading 1 byte at the program counter, and here we are reading 1 byte at the program counter. 1 plus 1 gives us 2. So the decode stage, do we need to read from registers? Yes, we do need to read from registers because we're doing a register to register move L. Right, we're reading what's in register A, and we're going to write that to register B. So val A, right, we store the value in this thing called val A. Arrow sign, register RA. Okay, and we don't need a val B because we're only going to write to register B. We don't have to know what is in this register. Execute, this is where any math happens. We'll say val E is going to be equal to val A plus 0. For the memory stage, are we reading or writing from memory? And the answer is no. Right? We are solely dealing with registers up here. You don't see any of this nonsense. RB. Right? This would imply memory. Neither of these are memory, they're both registers, so we don't have to do anything with memory. And then writeback stage, so this updates the registers. This will say register RB is going to be equal to val E. Okay, so we took what was in register A and we read that value. We moved that value to val E, and then register B will be set equal to val E. Then PC update, the program counter will equal val P. And this happens every time as well. The next guy is op-L, and this stands for operation L. So operation would be like add L, subtract L, or like XOR L, and ... I think there's a handful more. But these guys are determined by the function. Okay, this guy, and this guy, they're determined by the function. So we said there's iCode and iFun. Right, so for operation L, I know that it is 6. And then iFunction determines which one of these guys it is. So this is like 0. This is like 0, 1, 2, 0, 0, 0, 0. So this would be 0, and this would denote add L. So for the fetch stage, we always have iCode and iFun. iCode, iFun. This will be equal to 1 byte in memory stored at the program counter. Then, do we have any registers? Yes, we do have registers, register A and register B. And this will be 1 byte of memory stored at the program counter plus 1. Do we have a val C? No, we don't have a val C because we're only dealing with the values in the registers. There's no $5s or constants or anything. And then val P, this will be equal to the program counter plus 1, 2. So plus 2. So we're doing an operation. So let's say we're going to do add L, just to pick one of these things. Add L. So to add these two registers, we need to know both values. So we're going to need val A and val B. Val A is going to be equal to what is stored in register A. And val B is going to be what is stored in register B. Execute. So this is our math. So if we're doing add L, we're going to add these two values. So val E will equal val A plus val B. Then do we have anything to do with the memory stage? No, there's nothing to deal with memory here. And then writeback, Yes, we do have to write this back. So the way an addl works is if you've got RA and RB, you add these two registers and then it stores it in the second register. So we need to write to RB. So register RB is going to be equal to val E. Then PC update, program counter will equal val P. Alright, so the next one. So this was taken from an old midterm exam, and this is basically a simpler one of these guys, where this was taken from an old 271 exam. So let's see if we can try and figure this out. We're trying to increment register B, so that would just be like inc EAX %. So in the fetch stage, we definitely need icode and ifun. Icode, ifun. This will always be stored at 1 byte in memory at the program counter. Then, do we need to read from registers? Do we have any registers? Yes, we do have a register. RB. So RA, RB. This will be equal to the 1 byte in memory at program counter plus 1. And do we have a val C? No, we don't have a val C. All we're doing is incrementing this. Then the last one is val P. So val P, and this guy will equal the program counter plus 1 byte, 1 byte, 2. Decode stage. We're going to increment RB, so we will need to read from this register. So val B, this will be equal to what is stored in register RB. In the execute stage, val E will be equal to val B plus 1. Memory, we don't have to write to memory. And then writeback stage, we need to take this new value and store this back in register B. So register RB will be equal to val E. And PC update should be pretty obvious. This one's PC will equal val P. So these are the 3 problems that I wanted to cover real quick. If you have any questions, go ahead and comment below. Or if you have any topics that you want me to cover, let me know and I'll try and make a video and shoot it out before the midterm. Thanks guys.